Royal Institute Christmas Lectures, Mathematics into Pictures, Lecture 1. Take 1, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3.
Well, welcome to this year's Christmas lectures, and a special welcome to all you young people. I think I'm right in saying that out of the 149 years that the Christmas lectures have been given, this is the first time they've been devoted to mathematics. And I guess this must be because they're traditionally devoted to science, and mathematics is not quite a science. It's halfway between an art and a science. On the one hand, it's the art of proving theorems, and on the other hand, it's the universal language of science. So what I'm going to do is, well, I can't really explain to you what mathematics is without actually doing it. And I want to do it in a special way. I want to seize this opportunity to do it in a special way. Just as a scientist fills this bench here full of experiments, I want to fill this bench here full of pictures. And I'm going to exploit your visual imagination so that you can see through to the heart of the matter by pictures. Well, I want to start with something for which we all have a very strong visual intuition. That's the notion of linking. This is the one I want. The notion of two curves being linked is a very fundamental thing, so fundamental that we're almost tempted to believe that we're born with this intuition. But in actual fact, I think we have to learn it by experience. I remember my eldest son, when he was about 6 months old, he was sitting in his bath one day, and he picked up a red ring, a plastic ring, and he slipped it on his arm by accident. And then a look of surprise came over his face, and he slipped it off again, and he slipped it on again, and did this about 30 times. And then gradually, his look changed to one of absolute delight. And I think that was the moment when he actually discovered the notion of linking. Well, you think you know what linking is, but before I prove any theorems about linking, I'd like to show you some party tricks, because there's more to linking than meets the eye, and I want to stimulate your intuition a little bit. So I need some volunteers to come and help me be conjurer's assistants. Well, now, okay, and I need at least 4. Okay, you, come forward, come down here. You come, and I think I've got enough now. 1, and will you come? Yes? Good. Now, what's your name?
Helen.
Helen, okay. And yours?
Christopher.
Christopher?
Adam.
So's mine. And Adam, okay. Have you got a pair of scissors, Bill?
Yes.
Haven't you got anything bigger than that?
Well, I think we have.
Ah, that's better. Okay, you come along over here then. So what I want you to do is to hold the scissors. Now I'm going to put a bit of string through the scissors. I'm going to link them through that end, and then put the 2 ends through the loop. And then we're going to bring the other 2 ends through this other handle of the scissors here. That's right. Now, Christopher, you hold those 2 ends and don't let them go, because he's got to try and get them off the scissors without you letting go. And you're allowed to cut them. Actually, these are not very efficient, I can assure you, but you've got to try and get them off the scissors without letting go. Okay, you have a go over there. And now, what's your name?
Richard.
Richard, and you were Helen. Now, have you got the other piece? Good. So I hope you don't mind being tied up, do you? All right. So I'm going to tie this round your wrist. So hold your wrist out. And tie this other end round this wrist. Yeah. That's not too tight, is it? Good. Give a yell if it's too tight. That's right. Now, Richard?
Yes.
Okay. Here we are. That's round your wrist. And now I'm going to link them and tie the other end round his wrist. There you are. And now you've got to get free. How are you getting on with the scissors there?
Okay.
You haven't let go?
No.
Good, good. Well, do you want me to show you how to do it?
Yes.
All right, then. What you do is you have to poke it through this little bit. Let's turn it around here like that. See, come here around here. Then we have to poke it through like that. Tied a bit tight, didn't I? There we are. Voila. Thanks very much. Okay, you can go back now. Can you untie them? You untie them. Now, have you got on? You've made it more than a muddle than it was before. Well, I'll tell you what. Why don't you go and try it at home this evening, and then find out how to do it, and at the beginning of the next lecture, you can come and show us how to do it. And if you can't, I'll show you how to do it. Okay, thanks a lot. So we'll hand them back to Bill. Well, now what I want to do is to show you how to think conceptually so you'll be able to understand how to do that trick of unlinking the two people themselves. You see, the fact that they were people doesn't matter. I mean, I could have just done it with two balloons, that trick of unlinking people. So let me demonstrate this as if Helen and Richard were two balloons. So here's Helen. There she is. And here's Richard. And here's his two arms. And here's the piece of string that was round Richard's hands. And now I'll put in Helen's arms. And the piece of string that was round her hands. Well, now you can quite easily see what to do. You see, to get Richard's bit of string away from Helen, all you have to do is to slip it in between Helen and her piece of string. It just comes out. So, of course, Helen's hands will be sticking a little bit through her loop. So as you bring it round here, you have to do a little wiggle round, and then it comes out. You see, so that gives you the conceptual understanding of how you actually take two things apart. Well, this branch of geometry in which we deform things down to their simplest shape, in which distance doesn't matter, and in which we do this in order to try and abstract the most fundamental properties of things. This branch of geometry is called topology, and it was invented in about 1895 by the famous French mathematician Poincaré. Now, it's obvious that linking is a branch of topology because when you move the links around, you don't actually change the linking, however much, it doesn't matter on the distance. So if we're going to develop a theory of linking, we must work with closed loops, not like the example of Helen and her piece of string. So to develop a theory of linking here, I've put out some simple examples of links. You see, the first example here is the two curves linked once. As you can see, the red curve comes around, and I've made a little break in the yellow curve to indicate that the red curve goes through the yellow curve and behind this horizontal bit of the yellow curve. So the red curve goes through once the yellow curve, and so we say this is a link with linking number 1. But now, look at this one. As the red curve comes round, it goes through the yellow curve there, and then it comes round again, and it goes through the yellow curve again, and then it comes round back to the start again. So this example, we say, is linking number 2. And here, we do it again. This time, the red curve goes through the yellow curve once, round, through it again, and through it a third time. So this one, we say, has linking number 3. And so it's all very simple. But now let's look at this example here. In this example, we've got the red curve going around 3 times and the yellow curve going around twice. Now there's a problem. What should the linking number be? Yes, what do you think? 6. How did you know that? You're quite right. Because how did you know it wasn't 2 plus 3 rather than 2 times 3?
Each of them is going through the curve twice.
Yes.
So it's 3.
Yes, you've hit the note on the head. You've got it right. Exactly right. Because it's going through twice. But if I draw a more complicated example, you wouldn't perhaps. I'd maybe defeat you. But you've got the right piece of intuition. You see, we can see it right back here. The red curve is going twice through the yellow one there, but how many times is the yellow one going through the red one? You see, it's difficult. It's not easy to see. It's not an obvious thing. So that's the first theorem I want to prove, is that this link is symmetric. That is to say, if I make this link out of hose pipes, I can actually interchange the yellow and the red curve. So that being so, since we know the red curve goes through the yellow twice, then the yellow will have to go through the red twice. See, because it's symmetric, and I know each one links the other way, the same amount. So that's the theorem. The first theorem I'm going to prove is that the 2-link is symmetric. Now, I know the word theorem actually makes some of you tremble, and maybe at the word proof makes your knees knock together. But don't worry. This particular proof I'm going to do entirely by pictures. I'm not going to use any numbers or x's or y's. And actually, I'm going to give you 2 proofs. I'm going to give you first a scientific proof and then a mathematical proof in order to illustrate the difference. Now, the scientific proof, I need an experimenter. Who's going to be a volunteer experimenter? Okay, come down with me. Now, what's your name?
Mark.
Mark. Okay, Mark. Then what we've got to start with is the yellow curve horizontal. So you hold the yellow curve out like that. You get there. And you hold the yellow curve out like that. And so we've actually got the red curve going around twice through the yellow curve. Now we've got to interchange the positions. So you let go of the yellow curve, and you take the red curve, and hold. I've got to bring this bit round. Let go a bit there. That's right. Now you take hold of the yellow curve. That's right. Now I've got the yellow curve going round twice, you see. So we've interchanged them. We've done the experiment. That's the end of the scientific proof. It wasn't too bad, was it? Okay, thanks a lot. Well, now I'm going to give you the mathematical proof. The mathematical proof consists of actually writing down that in symbols. Now, the best symbols to use here are just pictures. So I'm actually going to write down what we did in pictures. So we're going to start with that one. Then the next picture will be this one. You see, how I go from this picture here to this picture here is I take that little twist in the middle there, and I twist it that way, and that untwists it, and so I get this bit here. See, so that's the actual proof from going from here to here. Now, the next step will be this one. I take these two bits and I just straighten them up. So that gets me to this picture. See, that's quite easy to understand. Now, the next one, I take another copy of this. As you can see, that's exactly the same. And then I just turn it on its side. Whoopsie. Just turn it through 90 degrees. Well, now, what's happened is you've noticed that the red and the yellow curves here have actually interchanged. So where the red curve here was vertical is the yellow curve here that's vertical, and the red one, the yellow is horizontal, the red is horizontal. So I've now actually achieved the interchange. So having got that, I can then go back along this route here and get back to the start with the red and yellow curves interchanged. So that's the end of the mathematical proof. Well, I can see yourselves saying to yourselves, there's not a great deal of difference between the scientific proof and the mathematical proof. I mean, if I had done the scientific proof, all I do is watch what I'm doing and record it in pictures. And if I had the mathematical proof, I could just realize it as the scientific proof. So what's all the fuss about? Now, the answer is that when you're trying to prove two things are the same, then the maths and the science is very similar. But if you're trying to prove two things are different, then they're very dissimilar. So the next theorem I want to prove is that this 2-link is actually different from the 3-link. So, now how would a scientist approach this? And the answer is that when a scientist has a theory, suppose he tries to prove that theory by doing an experiment to disprove it, by doing an experiment which he tries to disprove it by doing an experiment with the opposite. So what a scientist would do would be to make a 2-link, and he'd try and move it into the 3-link, and then his experiment would fail. And then he'd say, okay, the 2-link's different from the 3-link. I've proved it. So that's the method of science. You try to disprove your theory by doing an experiment to prove the opposite. Then you fail, and that proves your theory. But at the back of your mind, you always have the reservation that some later genius may come along and do a more cunning experiment and disprove your theory. So it's always a temporary thing. So scientific proofs are not 100% watertight because they might be proved by some later genius coming along. I mean, Einstein came along after Newton for the theory of gravity. So for a mathematical proof, however, is 100% watertight. And once it's proved, then it stands incontrovertible for all time. So now I'm going to give you the mathematical proof that these two are different. Proof. Suppose not. Suppose they are the same, therefore we can move one into the other. All right, then move the 2-link into the 3-link. And then let L equal the linking number. Then the linking number is invariant. It doesn't vary as you move the knot around because it's a branch of topology. Now, the linking number of the 2-link, therefore, at the beginning of the move, must equal the linking number at the end of the move, which is the linking number of the 3-link. But we know the linking number of the 2-link is 2, and the linking number of the 3-link is 3, and therefore 2 equals 3, which is nonsense. So we've arrived at a contradiction, and therefore the supposition that we started with must be wrong, and therefore the theorem must be true. See? That's the mathematical proof. But I know what you're going to say to me is, I haven't defined a proper linking number yet. And I have to admit that's true. And then you're going to say, you haven't proved it's invariant. And I'll have to admit that's true, too. And then you're going to say, well, you haven't actually rigorously proved that the linking number of the 2 link is 2, or the linking number of the 3 link is true. And I'll have to admit that I haven't done that either. And I can see you're about to get up and walk out of the lecture. So what I'd better do is I'd better hurry up and prove that. So our task now is to define rigorously the linking number. What I've got to do is to replace that vague notion of going through by something precise. So let me take an example. Here's an example of a curve which is just the same as this original one that we had to start with. They're just linked once. But I've drawn it so that it's not at all obvious. You see, I've drawn it with this extra loop going down here so that it looks as though it links 3 times because it seems to go through 3 times. But in actual fact, it goes once through that way and back again, so that little loop here doesn't really count. But I've got to devise a method of defining linking number which actually copes with that. Someone on the telephone. We've got to define a linking number which actually copes with this problem of possibly going through 3 times. Now, here's the definition. Yes. I've got a bit of towel. No, we haven't. I've written on the thing. I meant to have transparencies to write on. Oh, well, not to worry. Now, the definition of linking number is like this. First of all, we're going to choose arrows on the curve, choose directions on the curve. Next, we're going to choose one of the curves, say B. Next, we're going to choose a surface, which I'm going to call beta, spanning this curve B. So those are the 3 choices. Choose arrows, choose one of the curves, and then choose a surface spanning it. So here, now, I've got the arrows. There's the arrow on A, and there's the arrow on B. Next, I choose the B. Now, I choose a surface actually spanning B. So here's a model of this surface spanning B. You see? There's B going around that way, and here's the surface. Now, what I'm going to do is to count the number of times this red curve pierces the yellow surface. Well, one thing I should make sure of, I've painted the top of this yellow and the bottom of it grey. Now, how did I know which was the top and which was the bottom? Well, the answer is that I've got this direction going by my arrow. I imagine a corkscrew driving through the surface with a right-handed corkscrew. Well, going through with the right-hand corkscrew, that's going to be the top and that's going to be the bottom. So this arrow actually determined which was the top and the bottom. Now, I've got my arrow on A, and as I come around A, whenever I pierce the top, I'm going to call it a positive piercing. So here's a plus sign for a positive piercing. Now I go down and come, and this time I come up. I come from the bottom. So I'm going to call that a negative piercing. So I put a minus sign on. And then I go around there, and I go down again through the top, so I call that a positive piercing. And then I add the number of pluses together, and it gets equal to 2. And I add the number of minuses together, that's 1. And then I subtract the minuses from the pluses, and I get 1. And so that gives me the answer, the linking number 1. You see, and what I've done is I've replaced this vague notion of going through by the precise notion of counting the number of times that the red curve actually pierces the yellow surface. So going back to our proper definition, now. We choose the arrows on the two curves. We choose one of the curves. We span that with a surface. Then we count the number of positive piercings, which in this case was equal to 2. Then the number of negative piercings, which in this case was equal to 1. And then we take the difference, and that's 2 minus 1 equals 1. So that gives us the answer. So now we can actually calculate some real linking numbers. So let's do the 2-link. Here's the 2-link. Well, here's the arrow. We go round, pierce it once positively, we come round, pierce it again positively, and come back to the start. So we've got 2 positive piercings, no negative piercings, so the linking number is 2. Next, we take the 3-link. This time, we come round here, 1 positive piercing, come round again, another positive piercing, come round again, another positive piercing, and there are no negative piercings, and so 3 positive, no negative, the difference is 3. So the linking number of the 3-link is 3. And now we can go back to this difficult one and prove your statement that the linking number is 6. So have you got a model? Here we are. Here's actually a model. Will you come and help me prove it? And we need somebody else. You come too, then. You see, here is the, we'll hold it round like this. Here is the yellow curve going all the way around, and we've spanned it with a surface consisting of this top disk and that little twisted bit at the back and the bottom disk. And since that was the way round of the curve, this is the top, and then we trace it down with a little bit of twist there, and so the top of this disk is also painted yellow, and the bottoms of both disks are painted black. Now, so you hold this, and you're going to go round. You're going to start here and go around that way, and each time you're going to come to a crossing, you're going to tell me whether it's positive or negative. Okay? So as we come to the top one, what's that? Positive, that's right. We put a positive on. That's right. Okay, then we go round, down here. You trace it round. You put your hand on it so you don't lose it. Positive, okay. There's a plus there. Yep. Then we go round. Positive, okay. Oh, we got a negative. Dear. Still, 2 negatives make a positive. So there we are. Okay. Positive, right. Okay, we've got another positive there. Yes? Positive, right. Good? Positive, right. Good. And you've done them all, have you? So, how many positives?
6.
And how many negatives?
None.
None. So the leaky number is?
6.
Jolly good. What's your name?
Nigel.
Nigel. And yours?
Derek.
Derek. Give him a big hand. Thanks very much. Well, you can see that our notion of linking number is both rigorous and practical. We can actually compute with it. However, there is one big snag. Supposing you came along and chose a different surface. I mean, supposing I chose a yellow surface, you might come along and choose the curve A and choose a red surface. And then you might calculate the linking number, you get a different result. And then we'd be stumped, who would be right? Would it be you or me? And so we have to prove a theorem. We actually have to prove that your linking number will be exactly the same as mine. So that'll be our next theorem. The linking number is unique and invariant. Proof. You see, I calculate the linking number, so I calculate how the red curve A pierces the yellow surface beta. And then I calculate that my linking number, L, is equal to the number of positive piercings minus the number of negative. Now, you choose a red surface, alpha, and you choose how the yellow curve B pierces alpha. And so you get a completely different linking number. So let's call yours L dashed. And yours is going to be the number of your positive piercings minus the number of your negative piercings. Now, the problem we've got now is to prove that your L dashed equals my L. Okay? So have we got a model? Now, where's that original picture of our curve? We've lost it, have we? Not to worry. Doesn't matter. Ah, there it is. Very good. Now, that was our original example. And so you're going to choose a red surface, which is this red surface here, spanning the red curve, and I'm going to choose my original yellow surface. Then I calculated my linking number with 2 pluses, there and there, and 1 negative. And then you're going to calculate your linking number. Here's the right-handed screw on your red surface, and here's the B curve coming down, and it pierces it once, so I have to give you 1 positive one here. There we are. Now, I've got to give a proof that will work for every possible case. And these 2 surfaces will intersect, and they actually intersect here, in 2 little green lines. Can you see the 2 little green lines? Here and here. What are those there? Oh, I need those in a moment. They're 2 little green lines. See? Now, I want to count the front ends of the green lines, but I don't know which the front ends are. See, to know which the front ends are, I've got to put arrows on. So how do I put arrows on? Well, there's a rule. I take some red, green, yellow axes, and I arrange the red axis so that it's in the direction of piercing the red surface positively, and then I swivel it about until the yellow axis pierces the yellow curve positively, and then the green axis will tell me the direction to put the arrows. So I now know how to put those arrows on the 2 little green lines. And I now know which are the front ends. These 2 things are the front ends. This front end was my negative piercing, and that front end was your positive piercing. Meanwhile, the back ends are both my positive piercings. And if you had any negative piercings, which you haven't in this case, they'd also be back ends. So I can write that down. The front ends of my little green curves equals your positives plus my negatives, and the back ends equal my positives plus your negatives. Well, now, of course, the number of front ends equals the number of back ends, so I can bring this down and put this equal, p dashed plus n. And now we have an equation. And if we take the ends across the other side, we've got p minus n equals p dashed minus n dashed. But this is just my linking number, and that is just your linking number, and so we've proved my linking number is the same as your linking number. Well, there's one snag about that proof is because supposing we both chosen to span the yellow curve, then what we would do, this proof wouldn't work and this model wouldn't work. So what do we do then? I'll tell you what, we get a third party. We get somebody else over there to come and span the red curve. Then your linking number is the same as his, by what I've just proved, and my linking number is the same as his. by what I've just proved. So your linking number is the same as mine. So we're through. So we've proved the linking number is unique, independent of the choice. Now, there's one other thing to prove, that it's invariant. That is to say, as we move the curves around, it doesn't vary. But that's easy, because if we move the curves around, then we can also move the surfaces around. And then the number of actual points that they pierce in move around with them. And so the number of points, the number of piercing points, stays invariant, and therefore the linking number stays invariant. So the theorem is proved. And so that's the end of theorem 3, and that makes rigorous our theorem 2, that the 2 link is not equal to the 3 link. Well, you can see it was quite a difficult proof, but you can also see the dramatic difference between the mathematical proof by logic compared with the scientific proof by experiment. Well, if you didn't understand that proof, don't worry, you may be more of a scientific turn of mind than a mathematical turn of mind. So if you are, I think it's about time we did another experiment. What I want to talk about now is Möbius strips. Does anybody know what a Möbius strip is? You do. Okay, you know how to make a Möbius strip. Okay, come down and we'll make a Möbius strip. So how do you make a Möbius strip? What's your name, by the way?
Sheila.
Sheila, very good. So we come along here and...
You give it it's a loop with a twist in it.
That's right. Well done. Very good. There. That's a Möbius strip. Now, do you know something else? Supposing I started to cut it like this, what would happen?
Well, if you cut all the way along, it'd still be one piece.
Very good. You know all about it. Very good. But supposing I put 2 twists in, what would happen then?
I don't know.
You don't? And what about 3 twists?
I don't know that.
Oh, well, look, I'll give you one with 2 twists. There's one here with 2 twists. Where's that? Here, this is number 2. So there's one with 2 twists, and you start cutting, and now we need some more volunteers to cut these ones. Come on, then. Who shall we have? Can you come out? Come down, then. Can you manage to come down? Well done. Now, you come down, and can you get out, do you think? There. Very good. And we need one more volunteer. Okay, you come out. Now, let's see. You've got the 2 twists, so I'll put you here. And what's your name?
Matthew.
Yes. Where's the original Möbius strip that we in? That's you. That's the 1 twist. You cut that one. Who wants the 3 twist? You do the 3 twist. That's that one. And you do the 4 twist. Now, there isn't one for you. Ah, we've got a big thing here. You bring the big thing. Now, you get along there. You've already done it. You hold it there and wait for a moment, because I want to show you something else. Now, this is another property of the Möbius strip. See? Supposing we take this little car and move it all the way around, what will happen?
It'll cover both sides.
Yeah, that's right, it'll come to both sides. That's right, take it round. It starts at the top here, and take it round. That's right, you come up underneath. Yeah. So what you've proved is the Möbius strip has only got one side. Very good. Now, can you tell me, how many edges does a Möbius strip have?
One on each side.
It's got 2 edges?
Yes.
Okay, well, I'll hold my finger here, and you start with your finger and run it round. Don't cut your finger. Ah, you come round the other side, haven't you? It's only got 1 edge as well as 1 side. You didn't know that, did you? Oh, well, now you do. Okay, thank you. Now, what's happened to yours? You cut the 1 Möbius strip in half, and it's all one long piece, just as Sheila predicted. You cut in half. What have you got?
I've got 2 loops, but they're not well, I don't think they're Möbius strips.
Yeah, right. That's right. We didn't start with the Möbius, but it had 2 twists. But they're linked, aren't they?
Yeah.
You didn't expect them to be linked, did you?
Well, I didn't know, because my dad's done this experiment, only I forgot how it worked out.
Well, now you know. Very good. And yours is all 1 bit, is it?
Yeah, and I've got a knot.
Oh, well, we'll put that, we must keep that. We'll put that in the top hat. Ready. Well, that's a secret one. You shouldn't have said that. We'll put that there and bring it out later with a rabbit. And what have you got?
2 links and
It-
twists in it.
How many times is it linked? What's the linking number?
2.
2, you're right. So you had 4 twists, and you got linking number 2. And she had 2 twists, and she got linking number 1. So supposing we had 3 twists. Supposing we had 6 twists, what would it be?
3.
You're right. And supposing we had n twists, where n was an even number.
We'd have half n.
That's right. Very good. Thank you very much. Okay. So that's what we're going to prove. That's right. Thanks a lot. So this is now the theorem that we're going to prove, the one which we, Sheila, deduced. It's a theorem. So if we start with a strip of paper with n twists, and if n is odd, and then you cut it down the middle, this implies you're just going to have 1 piece. That's what happened with the 1 twist and the 3 twist. And then if n is even, you're going to have 2 pieces, and they're going to be linked with linking number n over 2 times. So that's the experiment which we've done for cases n equal 1, 2, 3, 4, and we've now got to prove for the general case. So we'll start the proof with the Möbius strip. Here is the Möbius strip with 1 twist in it here, before I start. Now we cut it down the middle, and I want you to think now of it being very, very, very thin, so that I can shrink the Möbius strip almost onto its original red boundary. See, there's the, I'm shrinking it onto the red boundary here. I've shrunk that green line until it's almost negligible, you can't see it. And then, to make sure that that's all 1 piece, I've just untwisted that until I get a single loop. So the trick then, the intellectual trick of how to think about this problem topologically is when we've cut the Möbius strip, the cut thing behaves exactly as the boundary of the original thing before you cut it. See, once you establish that principle, then it's easy. Because if we take the, here's the, this is the 2 twist, and when I cut it, I'm just going to get its boundary, which is just 2 curves linked once. So you start with a 2 twist, cut it, and you get 2 curves linked once. Now we'll look at the 4 twist. Here's the piece of paper with 4 twists at each of these points. And when I cut it, I'm going to get the same behavior as its boundary. And you see the boundary is 2 curves. And this was exactly the figure that we had before when we were proving the 2-link symmetric. It was the middle figure. You remember? There were 2 copies of it. So that shows that you cut the 4 twist in half, you get the 2-link. And exactly the same proof then works for any even number. And now we come to the 3-link, this one in the top hat. Here's the 3 twist. But when we cut that in half, we get a single curve, but it's not a simple curve, it's actually tied in a knot. It's actually like this knot here, you see? And so when I pull it tight, you turn out to be knotted. So that's exactly what happens when you cut a 3 twist in half. And here's the one which we cut before, and here is the knot, knotted. See, now you didn't expect that, did you? What will happen if you cut a 5 twist? Yes? No, not quite. That's a good guess. You get something more complicated. Yes? What do you think you get? That's right, you get a more complicated knot. You're right. Here we are. There's the 5 twist, and that's his boundary, so that's the knot that you actually get. Well, of course, there's another problem here. To actually prove that it's knotted, and to prove that you get a different knot each time, then of course we have to go through the same tough kind of proof that we went through before. Instead of linking numbers, we have to define knotting numbers. And knotting numbers are a little bit more subtle, and the proofs are a little bit more cunning than linking numbers. Of course, I'd like to give you the proof that knotting numbers exist and that they're invariant, and I'd like to calculate for you that the knotting number of the 3-link is 3, and the knotting number here is 5. But that's another story. But if you're curious, maybe I'll include that proof when the lectures are eventually published by the BBC. But I remember, I must tell you a story. When I was a young research student, I was really fascinated by knots and knotting numbers. And I knew that you could link 2 spheres in 5 dimensions. And so I said, well, if you can link a sphere in 5 dimensions, surely you should be able to knot it. So I tried, like anything, to tie a sphere in a knot in 5 dimensions and actually prove that it was knotted using knotting numbers. But I failed, of course. But the thing kept bugging away at the back of my mind. And 7 years later, one Saturday morning, I sat down and I suddenly realized that you could unknot spheres in 5 dimensions. You can tie them in knots in 4 dimensions, but you can unknot them in 5 dimensions. And suddenly, and this is very typical of mathematics, when you're learning it, or when you're inventing it, or when you're discovering it, up to a certain point, everything is murky and confused, and suddenly you see the light. And all of a sudden, it becomes translucent. And this one single result about unknotting spheres in 5 dimensions led to a whole cascade of theorems in higher dimensions. And that led on to quite a big theory of geometric topology. Well, so much for pure mathematics. What I'd like to do now is to give you an application of this to biology. It's only just a little application, and in the last 3 lectures, we shall actually be talking much more about applied mathematics and about the whole art of modeling. But today, I just want to give you this one little soup song. The soup song, it's going to be about DNA. Does anybody know what DNA is? Yes. What do you say? It's very good. You said it right. It's deoxyribonucleic acid. Very good. It's the molecule. And do you know why it's important? Why? That's right. It's in every cell. This is the key molecule of which our genes are made. And this is the molecule in which heredity is stored. And the discovery of the structure of this molecule in 1953 by Crick and Watson was one of the most important discoveries in biology of this century. And what they discovered was that it's in a double helix. It's very complicated, there are lots of atoms, but the main structure is, you see, a double helix. Now, the reason why a double helix is important is because you can separate the 2 strands. And here we've made a simpler model. This is a simplified version of that. And I'm now going to take these 2 strands apart like undoing a zip fastener, with a bit of luck. Yes, there we are. Now, the reason why it's important is because each of these 2 strands then acts as a template upon which you can build another double helix exactly the same as the parent. So from this parent, you can produce 2 copies, and then these 2 copies can go to opposite ends of the cell, so that when the cell divides in the middle, you have 1 copy left in each of the daughter cells, and so heredity is passed on. So that's the secret. That's the very important secret of DNA. Now, of course, this this little helix here only has 2.5 turns. In actual fact, it could be 1,000 or even 1,000,000 times as long as this. But of course, that is not in a straight line, because when it's actually inside the cell, it's all wrinkled up. It's not only coiled in a helix, but it's coiled in supercoils. The helix coils on itself in supercoils. And we can actually see that in a photograph. Here's a photograph of a piece of DNA inside a bacteria cell. And you can see it's all coiled up. Look at all the little supercoils around here. Now, this particular piece of DNA is a plasmid, and it's believed that this one causes its host to be resistant to drugs. So it's a very important piece of DNA. Now, this one also has another important property, is that it's actually not a long line of DNA, it's actually a circle. The two ends are joined together, so you've got a helix going right the way around in a circle. How do we know it's a circle? Well, if we drop this helix inside the right kind of chemical, for example, ethidium bromide, then if we look at the next slide, we'll see what happens. It separates, it relaxes all that supercoiling and becomes a single curve which you can trace around and forms a closed circle. Now, there's other experimental evidence for DNA being in a circle like this, because there's a special protein which gobbles up the ends of DNA. See, and so if it finds a free end, it gobbles it up, and this protein is guaranteed to destroy any DNA that's going except the DNA which is in a circle. If you want a circle, the poor protein can't get its teeth in anywhere. There's no end for it to gobble up. So these circular DNA are resistant to gobbling by the proteins. And there are many copies of circular DNA. I mean, most bacteria have circular DNA, and most plasmids have circular DNA. And now we have a problem. Because imagine a circular DNA trying to unzip. It's exactly like one of the pieces of paper that we were cutting just now. So it's fairly important to know whether it's got to have an odd number or an even number of turns. You see, if it's got an odd number of turns, that when it unzips, it won't fall into two pieces, it'll still be in one piece. That's what you proved. So that'll be no good, because it's supposed to be in two pieces to get to the opposite end of the cell so that the cell can divide with a copy in each. So it must have an even number of turns. But now if it's got an even number of turns, when we unzip it, what will happen is it'll be linked. And we can actually work out the linking number, because we can calculate how frequently that spirals, we can calculate the length, and the linking number turns out to be about 27,000 for this particular plasmid. For some DNA molecules, it turns out to be over 1,000,000. Well, if it's linked with linking number 27,000, how can you possibly pull it apart to go to the opposite end of the cell, ready for the cell to divide? That's a real problem. Well, of course, biologists have faced this problem from early days, from as soon as they discovered the circular DNA, and they've had to postulate a particular form of protein which comes along, grips it, cuts it, pulls it apart slightly, holds this part tight, and swivels that, so it unswivels it. And they actually call it swivel-A's. Well, then you go to the biologists and say, how does the swivel-A's know to swivel it exactly 27,000 times, not 27,001? And they shrug and say, well, and then you say, have you ever seen it? And they say, well, it's too small. You can't actually see it's smaller than the wavelength of light. And they say, well, I know it's unrealistic, but if you start with this picture, and this is the standard picture in all the biology textbooks, then you've got to postulate something like swivel-A's to explain the separation. And so perhaps this is the wrong picture. They say you can't say a thing like that. That's standard biological dogma. But of course, being mathematicians, we can say something like that. What is the experimental evidence? Well, we saw the experimental evidence for it being a circle, this kind of photograph. So what is the experimental evidence for it being in a helix? So could we have the next slide? Now, this is the famous X-ray photograph by Rosalind Franklin, made here in London in 1953, which was the first photograph to confirm the helical structure of DNA. As you see, it's a very peculiar, it doesn't show a helix at all. What you have to do is to deduce by indirect evidence from this diffraction photograph that these horizontal bits here represent a helical structure of the underlying molecule. Well, as you can see, this photograph doesn't say it's got to be a helix everywhere. This photograph says most of the places it's got to be a helix, but at some point you could have a little kink like that. So the photographic evidence is for a circle and a helix most places, but not a helix necessarily everywhere. So what I want to propose to you is an alternative, not this picture, which is in all the standard textbooks, but an alternative model. Here's the model. Stretched on these 4 pegs, I've got 2 curves. And if you look closely, you can see there's an orange curve on top and a black curve on the bottom. And they're unlinked because the orange one goes all the way around on the top and the black one goes all the way around on the bottom. Now, to represent the molecular forces holding it together, I've bound the 2 together with this blue cord. So if I could cut the blue string, then since they're unlinked, because one's on top of the other, I could take one apart and take it to one end of the room, and the other apart and take it to the other end of the room, and that would correspond to the unzipping. So I've got 2 unlinked curves. But now, what about the helix? I've got to face the fact that there are molecular forces, as in the molecule, struggling to turn it into a helix. So how do I put the molecular forces into this model which will struggle to turn it into a helix? Well, to illustrate that, I need another volunteer. Okay, how about you? What's your name? Matthew. Okay, you hold this other end of this piece of rubber and hold it tight and stand back a bit. That's right. Now what I'm going to do, I'm going to put molecular forces, I'm going to put torsion forces into this rubber which resemble the molecular forces inside this helix which are trying to make it into a helix. And I do this by just giving it a twist. See, we're twisting it up. And so we're putting inside these torsion forces. And now I'll relax the tension a bit. And what happens is a little supercoil appears there in a right-handed helix. If we do it here, there's another one. See? It's trying to keep, because we put these torsion forces in, it's trying to coil up into a right-handed helix. Very good. Now, what I've already done is to put the twists in these 2 ready. But I'm stopping the twist from acting by putting it on these 4 pegs. So now I want you to take it off the 4 pegs. And there, it's coiled up. Can you see? Look closely. Can you see? Everywhere, it's in a right-handed helix. It's coiled in a right-handed helix, and it's supercoiled. See? Now, not only is that shape, thanks very much. Let's go back and look at the first slide that we had and compare it. You see the supercoiling here is exactly like the supercoiling that I've got in this model. So the moral of this story is that when you get scientific discoveries, one tends to get a scientific dogma. And the dogma is the pictures in all the standard textbooks, like this. But if you approach the problem with a fresh mind, and that's particularly the type of mind that mathematics helps to give you, then you can often see through and suggest alternative solutions and get an idea of new possibilities which you can then suggest to science. And that is the virtue of maths. It helps to suggest to science not only explanations of known facts, but new possibilities for science to go forward. Thank you. What about